Okay, so we are ready with everything. All right, so essentially, like we are talking about IPC, inter-process communication, with different ways, right? We have been doing that for quite a long time. One of the method by which we can have inter-process communication is by creating pipes. By creating pipes. Pipes are again are of two types, right? You have named pipes and unnamed pipes. Unnamed ones are useful. It is possible to have IPC between unnamed pipes only between related processes, between parent and child. Unnamed pipes, by creating them, it's possible for parent and child to communicate between them. That's what we have already seen. Similarly, named pipes, right, where you can give a name to a pipe, right? We can give a name to a pipe. Using this, what is possible? Even unrelated processes, unrelated processes can also have IPC. Unrelated processes can have IPC as a part of it. We have seen all these things. We have been writing programs in that particular aspect. Using fork and exec, you can create child process. This is one way anyhow. The other way is by using a kind of a P-open, right? So that also we have seen about how to do that. And then like we also have used sockets, right? Linux sockets or Unix sockets, either way. So by using Unix sockets, inter-process communication is possible. After that, Unix sockets are basically like only within the same machine. Within the same machine, it is actually possible. Even pipes also within the same machine. IPC within the same machine. Both the processes must be running within the same machine. If you want to have inter-process communication across machines, processes running across different machines, then you need to go for IP sockets. IP sockets. Here it is possible IPC between what? Two different machines, between processes running on even on different machines. Different machines. So all these programs we have been writing that, trying to understand all that we have done. Now that we have other alternatives to have IPC between processes running on the same machine. There are three different types of other IPC mechanisms. Three types. That they are exclusively named as IPC even. Right? They are basically shared memory. Right? By just having a common memory between the processes, so that they can access the same location, make changes, or access the data. All that is possible. The other one is the message queues. So even by using message queues also, processes can send and receive messages by using the message queues IPC mechanism. Then the next one is called as semaphores. Semaphores are mostly useful for synchronizing concurrent programs. When multiple programs are simultaneously trying to access a common area, right? So the data in that common area is likely to be like go into some inconsistent state, right? Whenever concurrent programs try to access the same location, some programs try to modify and some programs try to read. Then the data that the programs might be trying to read may not be consistent. You must have studied that in database management systems and operating systems, in all those areas where we normally call such areas critical section. Critical section within a process or within a program is the area where it is trying to access a common location, which is likely to be referred by other processes as well. So before entering into the critical section, it is a good advice to first ensure that no other process is actually using that particular common area. And for that, these semaphores are going to be very handy. Synchronization purpose. Main purpose of semaphores is to synchronize concurrent programs so that they can access a common area only when other processes are not using it. That is the purpose of semaphores. Hope all of you are there, and about 12 students have come, and I think we will proceed. So that is about the three different types of IPC mechanism that we will be studying in the coming classes. And for all these, naturally, like all of them are available in the form of what is called as system calls. They are all available in the form of system calls. We are now again coming back to C language. Back to C language. Okay, so in this context, let me open the book. Let me open the book. And that will contain all the details. Yes, beginning the next program. So in this, what we are interested is IPC. IPC is okay. So IPC is here. Inter-process communication pipes, semaphore, shared memory, message queue. 577, right? So that is the base number. It may not be exactly 577 here. It may be a little more, about 600, let us say. So chapter number is 14, right? So we have to still further proceed. I think this is good enough. Font size and all that. We are in the 13th chapter. We need to proceed to 14th chapter. Summary. So we have come to that. This is the one. Semaphores, shared memory, and message queues. Right? So you can see we can cover the following and all that. He is talking about semaphores for managing access to resources. That's what? Managing access to resources. Resource is a common resource, basically. Shared memory for highly efficient data sharing between programs. That is the purpose of shared memory. Data sharing between programs. It is very highly, like essentially when you want to share large amounts of data. Large amounts of data. Small amounts of data by using messages and all you can handle. But large amounts, shared memory is the best choice. Messaging for an easy way of passing data between programs. No doubt, messaging, you can pass the messages and all that for passing the data, no doubt. But the data is mostly of limited size here. Whereas shared memory, you can even share large amounts of data. Semaphores, in order to give controlled access to these particular resources. That is the mechanism. But today's class, we will not go into semaphores. We will start with shared memory, actually. We will start with the shared memory. Right. So this is the one. This is the shared memory. Shared memory is the second type. Second of these three, whatever he is talking about, it allows two unrelated processes. Remember, unrelated means like what is the related example? Related example is parent-child.
Parent-child.
Right? Here, unrelated processes to access the same logical memory. Shared memory is a very efficient way of transferring data between two running processes. Right? And then you are going into that. Shared memory is a special range of addresses that is created by IPC for one process and appears in the address space of that particular process. Anyhow, so all that is there. We don't have to worry too much. But take a look into the diagram here. Take a look into the diagram. Diagram is not fitting into this. Right. So this is the diagram that you try to understand. Like there are two processes here. This is process A, this is process B. Every process requires its own memory. We know that. So, assume this is the physical memory you are talking about. And all of you are aware of there is something called logical address and there is something called physical address. Virtual memory management, basically. Right? So, the process A has got, requires, let us say, about 4 blocks. 4 chunks here or 4 blocks. Process B requires about 5 blocks or 5 chunks. Definitely, these are the logical addresses, but they need to be mapped to a physical address. So here diagram is given where this is mapped to this particular chunk. This is mapped to this. You can randomly put, you don't have to remember the diagram as it is. Right? So this is actually mapped to this. Similarly, the last one here is mapped to a shared memory. Remember that. We are actually interested in this particular topic. So all the other area of the memory, that is the normal memory you are talking about. Whereas this one is actually attached to this particular logical address of process A is attached to this shared memory. There is something called attach, right? A concept called shared memory attachment. Similarly, this process B has got its own chunks and they are actually mapped to physical memory. Remember, only the shared memory is the only thing that is actually common to both process A and process B. All the other memory areas, physical memory areas, are exclusive to process A and process B. Now, when it comes to this particular thing, like when process A tries to write something onto this area, onto the area of this particular thing. It is equivalent to writing on this shared memory. Similarly, process B, whenever it tries to make any changes or it would like to write anything on this area of the logical address space, this is equivalent to making changes on this. Or similarly, reading the data from here is equivalent to reading the data from this shared memory. So this is the central idea or the concept behind the shared memory. So you have a process, you have some mechanism where you can create a shared memory and attach that shared memory to a particular process. Any number of processes can attach. Remember, this example is only 2 processes he has given. But you can have another third process, its own memory, and shared memory is connected to like one of the blocks within that particular. There is no limit on the number of processes that can be attached to this particular thing. No limit in the sense, not like 2, 3 kind of thing. That's what I'm. So always, whenever anything is physical, their limits are bound to be there. But those limits are large numbers, like which are available, which are configurable kind of thing. So this is about the shared memory now. Now we need to study them. What are the system calls? What are the APIs corresponding to that? Names of the functions, similarly parameters required, and how are you going to write a program and ultimately see all that. So that's what we are going to study in today's class. So the coming on to the actual process, all the system calls related to IPCs and all that, they are made available as a part of as include sys/shm.h. So whenever you want to use any of these system calls, you have to include this particular header file. Remember, for shared memory, it is called as shm.h. For semaphores, it is called as sem.h. For message queues, it is called as msg.h. Like that, depending upon what system calls are you using, you have to include the corresponding header file. Shared memory is available in sys/shm.h. These are the actual APIs or the system calls whose signatures are completely given. Essentially, there are 4 different functions or 4 different system calls, of which the first one normally, even though in the list he is giving in the a different order, but let me actually talk about this. This is the first thing that you have to use. SHM get. Get one shared memory. That's the purpose of this. Get a shared memory. That means you can actually create a shared memory and then get one such thing. It is almost like whenever you are about to use a file, you open a file. That is a starting point. And after that, the actual usage is going to be there in read, write, seek, right? That kind of other system calls, where the return value of open is used in the read, write, and other system calls. Similarly, SHM get actually gets like it's going to likely to create a shared memory, or if it is already already created, you can also have like what it is an ID against that particular thing. You can get one such thing by using the SHM get, and it returns an integer. Whenever it fails, as usual, it returns -1. If it is successful, you get some positive integer value. So how are you going to use this? There is something called key against this, right? Key is there. So this key is unique actually. We try to define in that particular stance. So for every key, if you use the same key, you are going to get access to the same shared memory. That is what you really mean by. So all the processes, whenever they want to work on the same shared memory, they have to understand on a particular key value. It is a number basically. It is an integer value, right? So that you have to understand. So, and there is nothing like you will have only this many number of keys and all that. It's not like a port. For network port, there are fixed number of ports, number one. And once a port is given to one process, that port will not be given to any other process. It is an exclusive access for a particular process. Whereas here it is not like that. It's a number. Just to know like which shared memory are you interested, you are indirectly telling that indirectly through this particular number. Okay. So parameters and all will come to that. That is about the SHM get, shared memory get. After doing this, normally the next process is attachment, shared memory attachment. After getting this ID, whatever ID that we get, that ID you will be using as the first parameter to SHM80. Shared memory attached. That's what you really mean by. So with that particular ID, you are actually trying to talk about and get what you are trying to attach the shared memory to be a part of your process. Until such time, shared memory is available outside of your process. You can't directly access that. Only when you actually attach that to your process, then it is available through one of the addresses actually. And that address it returns. What is returned by SHM80? It returns an address as you can see, void star. It is returning a pointer to void so that it can be typecast to any pointer to any other type. You can typecast this address to point to any other address. It can be a starting address of a structure, or it can be a starting address of an array where there are a number of items. It is up to you about how to use that shared memory. What kind of data you want to store there depends upon your application. But starting address of that bigger chunk is going to be available, is going to be returned by this SHM80. And you are also passing on the second parameter here to that. And essentially, most of the time, this second parameter is going to be a null value. Remember that. It is a null pointer. Only when you give a null pointer, it actually identifies. SHM80 identifies a free memory so that it's going to return one of the free available main memory address. And that address is going to be returned. But there is another way also whereby you yourself are going to choose what is the address where this must be attached. In such a case, you have to specify the address here. If you specify the address on your own, then SHM80 tries to attach that shared memory to be the starting address of this particular address. But many a times, the good practice is that you give a null value here so that SHM80 returns, it is going to calculate and return the available, any available starting address. And that is going to be returned. That's a good practice. Flags you have anyhow, we'll see that particular thing and all that. Flag. So essentially the process is first you try to get a shared memory and then attach it. Once you attach it, then it is available at that particular starting address. Then once you know like the starting address, by using the C language, you can either read the data from there or write values onto that particular thing. That is about SHM80. You can use for as long as you require. Once the usage is over, then you want to like clear the things, right? Once the, let us say you are working on files, you open it, you use by using read write several times, ultimately you close the file by using the close. Similarly, here, similar mechanism is something called detach. Shared memory detach. Attachment, you are bringing the shared memory to be a part of your address space. Detachment, you are again detaching that particular shared memory address so that you cannot access the shared memory. So what is the system called here? SHMDT of what is to be passed on? Pass on the same address. The address returned by SHM80, whatever address it has returned, if you pass that address, then that corresponding shared memory is detached. And DT returns integer value. If it is -1, it has failed. Otherwise, like it is successful. That's what you really mean by. And then the fourth one is SHMCTL, control, shared memory control. SHM CTL. So for this again you have to talk about shared memory ID, meaning that what is the shared memory that you are talking about indirectly through shared memory ID. Main purpose of this shared memory control is basically one way is you have created a shared memory and the usage is over. You want to get rid of it. You want to remove it. And that removal is possible by using SHM CTL. You can remove the existing shared memory for some reason if you want. Or you want to change the permissions. That is also possible by using SHM CTL. So all that is actually there as a part of that. So these are the 4 system calls that you need to get used to it and all that particular thing. So that is about the 4 system calls. Now we can slowly get into developing a program. Essentially client server programs, right? We are actually talking about. Here also we will be developing 2 programs. And he is actually talking them as producer program and consumer program. One of the program is going to produce an item, produce the data, and store it into the shared memory. Consumer program is going to consume the data or read the data from the shared memory and use it for whatever purpose. So there are 2 programs you have to develop here also, right? So this you can see here. Now coming to the parameters and all that also you can talk about. SSM get first key value. Just now we have already talked about. And then what is the size of the shared memory that you want? Size in terms of the bytes. How many bytes of the memory are you interested? That you have to specify as the second parameter. It's a number basically. And then the third parameter is shared memory flags, meaning that these flags will talk about what kind of permissions, right? What are the permissions with which you want to create the shared memory? Meaning that just like files are there, you try to open a file and create a file with a particular permissions like read, write, execute for the owner of the file. Similarly, read, write, execute for the group members, read, write, execute for others of the system within that. Similarly, here also, that kind of control is possible by using the shared memory flags. And here within the same, we also use something called IPC create. Essentially, whenever a process would like to create the shared memory, if it is not there, if it is shared memory is not there, you also want to create it. Then you are going to use IPC create option also as a part of it. Added with the permissions. Permissions are mostly given essentially in C language and all that by using the octal notation. Octal notation. Octal numbers are specified in C language by starting with 0. If any number starts with a 0 in C language, whenever you are writing, that number is represented in octal notation. And it is easy to define permissions by using the octal notation, because read value is 4, write value is 2, and execute value is 1. So depending upon the combination, you can always find out 4 plus 2 plus 1, 4 plus 2, 4 plus 1, whatever. It is basically a 3-bit number. So 3-bit is equivalent to octal. That's why all that mechanism is there as a part of it. Then the attachment, SHMAT. So here you can see, specify the shared memory ID, and then the null value, mostly the second parameter. And this is going to be the flag. And this third flag actually, even though you have created the shared memory there, but at the time of attachment, you can also talk about whether you want to attach this in a read-only mode or even write mode kind of thing. So even though shared memory you have got, as per that you may have the permission, but you don't want, for example, as a part of your application, your program definitely is not going to make any changes to the shared memory, but it would like to only read the data from there. Then you can attach that with read-only option. You can attach that with read-only option. That is what is actually available here. As you can see, shared memory flag is a set of bitwise flags. The two possible values are SHM R and D, shared memory round, which in conjunction with SHM ADDR controls the address at which shared memory is attached. For efficiency reasons, the starting address, if it is exactly divisible by 8, divisible by 16, divisible by 32 kind of thing, the access to the memory, main memory, is going to be fast. That's why the starting address of the shared memory should always be a rounded one. That's what he is actually talking about. SHM underscore R and D. If you want, we can use that. Similarly, the other possibility is SHM underscore RD only. This is read only kind of thing, which makes the attachment memory read only kind of thing. Right? So that is about all this. And whenever attachment fails, it also returns -1. Remember that. -1 is returned whenever shared memory attachment fails. And we can examine that and all that. How do you use read-only kind of thing? This is one of the ways. SHM flag and SHM underscore RD only. Meaning that you are attaching the shared memory for read-only purpose. Okay, so this is over. And then detach is straightforward. There is hardly anything. A single parameter. Simply specify the address, starting address of the shared memory to SHM DT. And it's going to detach. Similarly, SHM CTL, this is slightly involved one because there is a data structure that is involved and several other things are there as a part of that and so on. Now, if you see here, SHM CTL off, first is the shared memory ID, no issue. This you understand. But then what kind of command, what kind of control are you interested, right? So there are different commands for that. Second one is a command. And based on this command, this third parameter will actually hold. So using the command, you can get the data and set it into the data structure here. That is one possibility, right? You are trying to get the attributes. Similarly, you want to make changes, in which case here the command will be there. Then here, whatever the details that are available here are going to be set to the shared memory as a part of that. So what is the data structure related to this SHM ID underscore DS? This is the structure of that. Essentially, you have the permissions here, nothing more than that. Just like you have permissions for a file, owner of the file, group ID, that is user ID, group ID, and what? And the permissions more. Similarly, here also, this data structure contains these three fields. SHM perm.uid, SHM perm.gid, and then SHM perm.mode. Mode is it, just like mode is there for the files also. Permissions mode, basically. CH mode, we have already tried, that kind of stuff. Right? So these are the things. Now we have to understand what are the commands, what are the different possible commands that one can give. Right? That we can look into that. Commands are the following. These are the three commands. Essentially, these are the constant values. You can pass on the value also, but remembering the values is difficult, but that's why you are giving the command names, macros basically. These are the macros. So IPC underscore stat, the command can be, one of the command can be IPC stat. That means you are trying to get the status of the structure of the shared memory, right? Sets the data in, even though he is using set here, he is setting the value of the data structure actually. But he is getting the data from the shared memory. Not the actual data, but the permissions, that kind of other stuff. Sets the data in the SHM ID DS structure to reflect the values associated with the shared memory. So you are trying to get the status of that particular shared memory by using IPC stat. The other one is IPC underscore set. Here, you are going to update. You are going to take the data from a data structure and update. So you can see here, set the values associated with the shared memory. Right? Here you are setting the data structure related, whereas here you are setting the values associated with shared memory to those provided in the shared memory in SHM data structure as a part of it. And all this is possible only when the process has got the permissions naturally, because it's almost like a file kind of thing. So whoever only like whoever has created the permissions for that particular thing, they can actually do that. So to get the permissions and the related thing and to make changes onto the permissions, these two are used. Whereas you want to get rid of the entire shared memory segment, then the command is IPC underscore RMID. This IPC underscore RMID is going to be used even in the other IPC mechanisms like semaphores, message queues also. This kind of control is there even for the other two. Here you are actually controlling shared memory, SHMCTL. Similarly, you can control the semaphores. You will have SEMCTL. Similarly, you can control the message queues. So while doing those things, second parameter, even there also is going to be a command. And one of the command there is going to be IPC underscore RMID. Purpose of this is to simply delete the corresponding IPC object. Right? The third parameter, buff, is a pointer to the structure and all this, right? Parameters, all those. So this is about actually a brief overview of the four system calls that are a part of the shared memory. Now that before actually starting to design a client server program or consumer producer program or whatever, we must first decide about what kind of data are you going to what it is share. What is the kind of nature of the data that you would like to share, and how much data are you interested, right? That you must decide. For that, in this example, there are two programs here as a part of this, and the two programs are SHM1.C and SHM2.C. So 1.C is a consumer program, 2.C and 2.C is a producer program. That's what you have to understand. The first program is a consumer. That means it's going to consume the data from the shared memory. That means only when the data is available there, meaning that if the producer has already put the data there, and that data can be accessed by the consumer. And how to handle that and all that particular thing, whether data is available there or not, right? So such kind of to control that, to know whether the data in that shared memory is available for the consumer to consume, right? So we are going to use one more field there as a part of that and so on. So here, the example given here is, he is actually building a small structure, C language structure. Some name he is giving, it doesn't matter whatever name that you want to give. Struct shared use ST. This has got nothing to do with the shared memory there. Like this is, depending on the application, this is going to change. So as a part of this producer consumer problem, is actually what it is, your shared memory is going to be a structure, a very large structure. How big is this? Let us see. So there are two fields within the structure. The first field is an integer value, and the second field is the string actually. It's a large string, about 2048 byte character string. So that means the producer consumer programs are going to store the data there and inform the other process, whatever. So now which process can actually use this is decided by this particular field. If the value of written by you is 0, means that one process can use it. If it is 1, the other process can use it. We'll see that, like what is the, like 0 means what, 1 means what, we will look into that. Only that particular process only is going to use it. It is a kind of a cooperative process, remember that. Cooperative process means they are designed such that they cooperate with the other process. That means they try to synchronize access to that particular common data in a proper way. Otherwise, if they want, they can directly access also without informing the other process. But results are not guaranteed in such kind of mechanisms. So here, this defines a structure to use in both consumer and this thing. You use an integer to write to tell the consumer when data has been returned to the rest of the structure or whatever. All that he is actually talking about. Right? So now we can slowly get into the actual program. So first it is number 1. What is the program number 1? Is the consumer program. Consumer program. First declare all the header files required. Right? And then sys/shm.h. And then in order to be consistent, you are also keeping this particular declaration, this entire thing. You are storing this entire thing into a file called shm_com.h. You are creating a header file, right? So that the same header file will be used in both consumer program as well as producer program. So that both of them will work on the same fields, basically. That is what you are actually doing that. So all of you are getting my voice? Is it everything okay?
Yes, sir.
Okay,
Yes,
right.
sir.
Thank you. So you are basically now, see, without doing also you can, by just simply typing all these lines in both the consumer program as well as the producer program, you will get the same result. But instead of that, what he is doing is, he's storing all this into a file called shm_com.h and then include that header file in both consumer as well as a producer program. That is the only approach that all of you need to understand. And whenever you want to include your own header file, if it is a system header files like these things, you have to use the angular brackets as include less than and then the header file greater than. Because they are, you are indirectly telling to the C language that include the header file whose content is this following thing. So these header files are actually stored in some fixed directory. The compiler knows the moment you talk about this and search for this particular file in the include directory. Whereas your header file, what you have created, is available in your own directory now. So in order to include your own header file, you have to use the double quotes here. Whenever you are including your own header file, you have to use the double quote, not the angular bracket. Right? So this you must exercise, careful exercise, you have to do that. Now let us actually go into the actual program writing. Actual program writing. Already you are familiar now. What is the purpose of this program? This is a consumer program. There is another producer program. Consumer will wait until the producer places the data into the shared memory. And whenever the data is available, only then it is going to use it. Okay, let us now go through the program. Int main, this you are already familiar config. They begin int running equal to 1. So that means just like the server programs we used to write, run them forever, that kind of stuff. So you want to run it until the what it is, the IPC is actually done with. For example, we used to have client server programs used to interact until the last string is end kind of it. So whenever you enter end kind of it, then the client understands this is the end of it. It also informs the server that this is the end of its communication, right? Something like that. So int running equal to 1. Similarly, void star shared memory equal to 0, null value, right? This is a null pointer actually. This is basically a null pointer. So you'll understand the purpose of that and all that anyhow as we move along. Definitely we require a shared memory variable. Similarly, we also require a like a structure, right? Because our shared memory is a structure. So we must have a pointer to hold that particular structure address. So for that, this is the one. Struct shared underscore use underscore st. This is the name that he has given actually. Complex name that is there within the com dot. So same name. You can use if you want. It can be a simple shared st kind of thing also. He's again saying shared use st and all that. So if you have to use the same name as somebody else, you may have to remember that. But it's not required. Whatever name that is convenient to you, you can actually give it. So struct followed by that structure name followed by pointer to that. Because ultimately you are going to store the starting address of that structure. And using that, you can access any of the fields because by using the pointer, structure to pointer and then fields within that. You are already familiar with that particular. And then int shared memory ID. Because SHM get returns an ID and that must be stored in some shared memory ID, SHM ID. And then he is also using some what we call random number related library functions. Basically to simulate consumer producer simulator. So consumer might take some time to consume the item. How much time? So that time you actually randomly choose and wait for that much of time. As if some big logic is there in order to consume the data, do a lot of processing there and all that. So such simulation he is actually trying to do by using random number related thing. So SRAND is a is the very first library function to be used to use the random numbers and all that is SRAND. SRAND stands for actually you are seeding. You are starting your random numbers by providing a number as a seed to that. Depending upon what number that you are providing as a seed, your random number sequence will change. Remember that. Even though they are actually called a pseudo random. You start the SRAND with the same number. You will keep the same numbers. In fact, you will get the same number sequence, right? Every time that you run, you get the same number sequence. But if you change the random seed, you will get different random number sequences. Anyhow, so that is a different subject altogether. You can understand that. But essentially, SRAM requires one number to be passed as a seed, any number. And generally, it's a good idea to give a random number. How do you get a random number? So to start generating random sequence itself, you are asking for a random number, right? So for that, the best use here he is talking about is process ID. Because every time that you run the same program, you get different process IDs. You get different process ID every time that you run it. So that means your random seed, starting number seed, is going to be different. So that's why you get different waiting times and all that particular appear. So for that, what he is doing is get PID. Already you are familiar with get PID. Get the process ID, essentially. And that you are passing on to SRAM. And later you are going to generate the random numbers and wait for that much of time. Maybe a sleep or whatever, that kind of stuff. Right? So now after that, SHM ID equal to SHM get of. Now the key value he is considering is 1, 2, 3, 4. It can be any number, except that both consumer and producer must use the same number because they want to work on the same shared memory. It is as simple as that. And because it is a, you are typecasting it to key underscore t. because this is a number, integer by default, but you are typecasting integer to key underscore t. So that no warnings also, no errors are going to come at the compilation. That's all what. And after that what? How much memory do you require? As much memory as the structure. Our structure is there, structure size. So that's why you say size of struct shared underscore use underscore st. This is the amount of memory that you require. And then permissions and all that, third flag, third parameter. Octal 666. 6 means 4 plus 2. Reading and writing. So the owner of the file, owner of the shared memory can perform read and write. Group members read write. Others also can perform read write. So such kind of permissions you are actually creating. And because if the shared memory is not yet created, you also want to create. So that's why you are performing bitwise or with IPC create. Bitwise or with IPC. If the shared memory is already there, it doesn't create. If it is not there, it's going to create. It is as simple as that. That is the purpose of IPC create. Even while creating files also, we do the same logic. And then we want to confirm whether it is successful or not. If SHM ID equal to -1, there is an error. So you display the error message. Fprintf of standard error, SHM get failed, exit of exit failure. Either this logic you can use, or you can as well use P error of SHM get failed. That is a much easier mechanism. Instead of using fprintf, use P error of SHM get failed. You're already used to that. It's up to you, whichever is convenient. And then you are terminating the program. Because shared memory is not there, then you can't continue the remaining thing. So you terminate. And once, yes, you have got an ID, now you have to attach that so that it can be used as a part of that. So you say now SHM80 of SHM ID, comma, next parameter is 0 as we said. And it should be void pointer, so you are typecasting it to void star. Third parameter also 0. Third parameter also 0. So this is SHM80 returns a starting address. Starting address of the shared memory. That's why you are storing it into shared memory equal to all this. Now in case it has failed, it returns -1. So you verify. If shared memory equal to void star -1, because it is pointer, so -1 will typecast that. That means there is an error. So again, you display that. You have printf this and then terminate. Terminate the program. If everything is all right, now the shared memory is attached to your process and it is available at so and so address, shared memory. This is the starting address of that particular structure. Remember, the structure is existing there. You imagine as if a structure is existing. And within the structure, you have the fields. The first field is the integer field, the second one is a character array. You are only printing here just to inform the user that this is the address where the shared memory is attached. So you can print that memory attached that %x. %x normally we use in order to display the pointers and all. You also have %p also. %p also you can use for printing the pointer values. Right? And after this, now what to do? Now that we have attached everything, right? So now try to get that as a part of our structure now. Right now, shared memory is a void star actually. So now this shared memory value must be stored into structure pointer. So you say shared stuff is equal to, and then you are typecasting it. Struct shared use SD star. This is a void star. You can't use this. You don't know the type of the memory there and all that. Now, once you typecast this, now this shared stuff is a pointer to our structure. Pointer to our structure. Now you can access the data within that by using the fields and all that. That's what he is actually using. So, consumer has created the shared memory. And then he's initializing, as you can see, with 0. Shared stuff hyphen greater than written by you equal to 0. That particular field is by u equal to 0. So consumer is initializing the written by u field with a value equal to 0. After doing that, what do you mean by that actually? If the value of written by u is 0, it indicates that producer can produce the value. That is the understanding here, right? We'll come to that. Now, producer can produce the item whenever written by u value is 0. So, consumer doesn't consume straight away now. He is going to wait actually. So, producer program also you have to run later on. So, both the programs must be running simultaneously. So, this fellow is waiting. The other fellow knows that written by u value is 0. So, if written by u value is 0, producer can produce an item. After producing an item, the producer will inform this by making written by u to become 1 actually. So this written by u value is right now 0 and it will be changed only by the other producer program. Now as you can see here, there is a loop, service loop. What is that this fellow is doing? While running. Running value is 1. Already in the top, you see running is equal to 1. That means it's a forever loop basically. It's a forever loop. Now what is that he is actually trying to do here? This fellow can consume it only when the value of written by u is 1 actually. So that's why he is verifying. If shared stuff hyphen greater than written by u. See, is actually using the value of this. If written by u. If this is true only when written by u is not equal to 0. But this fellow is not going to make any change. So if the producer is still not active, let us say, the value of this will be 0 only. If this is 0, it is false. So it doesn't come here. And again goes back while running. And once again verify. It is still false. Go back, go back. So it is continuously waiting. Once the producer program also starts working, that fellow will actually produce an item, write the data into this particular structure, and then change the value of written by u to become 1. So that when this fellow gets a chance, after some time, then the value of this written by u may be 1. Then this logic is going to be executed. Oh, then he is writing, oh, you wrote so and so string. Shared stuff hyphen greater than some text. There is a string there, right? So producer has produced this particular text. That you are actually trying to print. You can use it for any purpose. It all depends upon what is the purpose of these two client-server programs. So here there is no big purpose except that whatever is written by the producer is going to be printed here. That's all the main purpose. Once it is consumed here by the consumer, this fellow should inform the producer again that I have consumed it, so that you can produce one more and put it into the same area. That is how it is actually. So he is actually printing it, displaying or whatever, and then taking some time here. Taking some time, some random time. So sleep off. If you want to produce a random value, srand is to start the random sequence. Whereas rand will give you the next random number. So sleep off rand returns a random number, random integer value. And it's likely to be very big. So he is, you don't want to sleep for a very big time, right? If it produces 10,000 as a random number, you don't want to wait for 10,000 seconds. That's why he is limiting the waiting time to 4 seconds. When you perform mod 4 returns always the value will be between 0 to 3. So not more than 3 seconds sleep is going to take here. That's how it is actually, right? You are simulating that kind of stuff. So sleep for that much period. And after that what? What are you doing? The consumer is again allowing the producer to produce one more. That is why, as you can see, shared stuff returned by you equal to again 0. You are inside this because return by you value is 1. You are inside this. Now you are making it to become 0, so that producer also will be waiting there. If it is equal to 0 only, producer will produce the item. If it is equal to 1, producer will wait because it has already produced. Right? So that is the protocol that you are actually using. And then you also want to verify for how long should go on. If the producer has produced and put a value equal to end into that particular area, you want to terminate, right? Terminate mechanism. So you are basically comparing here. If strncmp of shared stuff some text, comma end, comma 3. So if the first 3 characters of this particular text is end, then you just simply terminate the program. Terminate the consumer. Producer also anyhow will terminate there in that particular. So how do you terminate it? By making the value of running to be 0. Once running is 0, you will come here and while running, it is false, so that it goes to the next step. If it is not equal to end, then it will still continue again. It will continue back. And again, like wait. Right? So that's how it is. It is a very simple mechanism. Once this is over, as you can see, the next step is to remove the shared memory. First step is to detach to begin with. So SHMDT, shared memory. This is a pointer, right? This is the starting address of the shared memory. That is a while. So you are basically detaching SHMDT of this. If this is returning -1, there is some error. Otherwise, everything smooth. Right? And after doing that, what are you doing? You remove the corresponding shared memory. How do you remove a shared memory? SHMCTLR, SHMID, comma, IPC underscore RMID. And then the next thing is going to be 0. So this is how you can remove the existing shared memory. By any chance, there is some error or whatever, is going to return -1. Right? If you fail to remove the thing. So you get all that. Ultimately what? Ultimately terminate the entire program. So this is how the consumer program is. It's a very simple program. Once you understand, there is hardly anything. Similarly, producer. Producer also now you can easily understand. It will be on exactly on the same lines, except that number 01 waiting time will be different for that particular thing. You can easily understand now. This is the second program, producer program. Include all the header files. Include this, our own user-defined header file. Right? Then the main logic. Running equal to 1. Void store shared memory, all that. Also structure starting address. And then what? This producer now is going to produce the items, right? Who are going to give you the data to be stored into that particular text and all that. So you have to read the data from the standard input, from the user. So if you want to read from the user, you require some array. So that's what you are actually doing. Cat buffer of buff size. This buff size is one of the constant that is already declared in the header files actually. You can directly use it. There is some standard size that it's going to actually declare. So buffer of buff size and then int shared memory ID. Now as usual, you can easily see SHMID equal to SHM get on. This entire stuff. 1, 2, 3, 4. So how much memory do you require? Same structure size. And then these are the permissions IPC create. So ID equal to -1, error message. After that, you attach. You are attaching that particular ID, comma, while attaching, second parameter is 0, third parameter also is 0. And if shared memory is return value is -1, there is some problem, terminate. Then print the message where exactly it is attached, starting address. And then In order to use this structure, you have to typecast this shared memory starting address to starting address of the structure and put it into this. And then while running, right? Now you can easily understand what you are actually there. Now you have to wait what? You have to wait for the client to consume the item. Wait for the client to consume the item. So you are actually doing exactly that. While shared stuff written by you equal to 1. If the value of that is equal to 1, what are you doing? If this is equal to 1 means consumer has to consume. Whenever its value is 1, consumer must consume. That is the indication we are using. So because like it is still 1 means this fellow should wait. So you are sleeping for 1 second. Here you are actually sleeping for exactly 1 second and then waiting for the client. This message you will be continuously getting until the consumer consumes the item and then stores 0 into written by you field. The moment consumer stores 0 into written by you field, as you can see, then what? So shared stuff written by you is no longer equal to 1. It is equal to 0. Then this will get out of the loop and come to this particular point. And then it is going to use, it is going to ask the user to enter a data. So user is producing the actual data in fact. Then whatever user enters, that data will be stored into that structure. And that will be printed by the consumer. Producer is reading the data, storing it into the structure, shared memory, and consumer will use it and then print it. Right? So there is a communication, right? Producer is communicating with the consumer via the shared memory. So how do you read the data? There are different ways. One is fgetS. Buffer not more than this many characters from the standard input. And after this what? You have to now copy this particular value that is available in buffer into the shared memory. How do you copy it? By using the same regular string functions, whatever. You can always do that. So you are using a safe copy, strncpy. So you are copying the value of this buffer into this text. Shared stuff hyphen greater than something. How many characters you want to copy? Not more than this many characters. That's why it is a safe copy actually. Otherwise, you can use strcpy also. But in strcpy, you can't mention the number of characters to be copied. Right? So that's why he's using strncpy of. This is the area to which you have to copy from this buffer into this, not more than this many characters. Because this is the only size that is available. If you want to store, try to store beyond that, then you are disturbing the program. So after copying the program, so the producer has produced the item and put it there. Its task is over. So now it should allow the other process to continue. So how do you allow it? By changing the value of written by you field. So shared stuff written by you equal to 1. And whenever it is equal to 1, you are allowing, the producer is allowing the consumer to continue. Right? And as you can see, not only that, after putting there, now he is also verifying, right? Producer must also verify whether this is the end of it or not. How do you do that? Same thing. If strncmp of buffer comma end comma 3 equal to 0, that means the end user, producer is like has produced all the items that it could, and there is no longer any data that is yet to produce. So once you reach this particular point, and all this, so it will get out of the while loop. So once everything is over, as usual, it has the shared memory. So creation of the shared memory is done by the consumer. That's why the removal also is planned in the consumer program itself. In fact, this fellow also can, like if permissions are there. So he is actually detaching that particular thing and then terminating the whole thing. That's all. These two programs, producer and consumer program. How do you run them? Compile, and then /SHM1 ampersand. So that the first one is the consumer. So consumer doesn't require any input from the standard input. You are not going to read. So that's why you are actually running that in the background. Run that in the background. Memory attachments also. Once you run that, and run the producer program in this foreground because it requires keyboard interaction. So memory attached that so and so. So this also is getting the same address. This will also is getting the same address. Now enter some text. Hello. This is the output. This entire thing is, this is the output of the producer, and this is the data that the user is entering. Once you enter hello, now hello is placed into the shared memory. Once you place the data into the shared memory, consumer will, after some time, naturally, he is going to give this particular reply. This is the reply from the consumer, in fact. Even though you're running here, remember certain things are the output from SHM1. So you wrote : hello. This is the output of SHM1. And then, like the other fellow, what? SHM2, producer, he's waiting there, waiting for the client. We are getting one more, waiting for the client. Probably that random number that is generated there is greater than 2 actually. He's waiting for more than 2 seconds there. And again, the producer has got access to that particular. Enter some text. The next exclamation. After some time, you're getting this. And then waiting for. Then you put all this. Right? Any questions there? Are you able to follow it?
Yes, sir.
Right? So with this now, we should be able to copy all of them into Genie or whatever, and then make necessary changes, and then run them as a part of it. I don't know. I think I have made something of that particular thing. If it is there, we can take a look into that here. Let us see. Programs. So IPC is there. These are the programs here. Message 1, SHM1.c, SHM2.c. We have SHM1 also, in fact. So there is hardly like I can show the program like by using Genie and all that. It's the same program. We can use that and try to like maybe develop other kind of applications and all that. So think of. So now if you want to run that SHM1, then run this in the background. So memory is attached that so and so. I have actually put something different there. So it's actually giving all this in hexadecimal notation. 0x, this is the address where it is actually attached. This is a consumer program right now. So similarly, producer program, you would like to run that. So memory is attached that so and so. See here, now the address is different here. Its address is different. Its address is different. You are not actually printing the address of the shared memory. Remember that. Shared memory is somewhere there, but you are now attaching that to be a part of your process. So within your process, it can be attached wherever it is available. So this is the address in the consumer, this is the address in the producer. Enter some text. So now it might be, so line, for me, easiest thing is no creation, line 1. See, you wrote line 1 and waiting for client, waiting for client. So now instead of displaying that as a line 1 as it is, you want the consumer to make, let us say, to receive that and display in uppercase. So such kind of functionality you can put it into the client. Or the producer is going to put some numbers there into that area. Client can read all those numbers and then maybe display the sum of all the numbers. Right? It is up to you now how to think of what data can go into the shared memory. Right? So similarly, today is Thursday, kind of entity is paid, something like this. He wrote all that. Then, so 3 times it has come now, whatever. So some other text or test is there. So, and remember 4 times also you have got waiting for client 4 times. So mod 4 only we have put maybe 3 seconds there, and apart from that one, you should not get more than 5 there, more than 4, definitely. No doubt about that. So immediately we have got wait. So like this, so you can, and ultimately, whenever you want to terminate, you terminate by putting end there, right? And after some time, this is client is terminated, and here this is also terminated. If you want to keep the producer like a consumer continuously, you can design so, right? It all depends upon how you would like your program to be designed based on that. So the program, if you want to take the entire thing at one place and all that, we can just take a look into the corresponding thing here. This is a shared memory kind of thing, like this. But before doing that, has includes this SHM and your own COM, whatever. And all the remaining programs you can see. So next portion, science and all that. We can remove all those comments. Whenever you remove all of them, the size of the program will naturally come down. Right. So this is the first program. Similarly, the second one is this. Is the producer. Right. So try to go through the book once again. Try to understand if there are any gaps. If you have questions now, I can address. And then write down the programs so that you can verify that, make necessary changes or whatever, all that. The next class, we will look into message queues to begin with, and after that, semaphores at the end, basically. I have also uploaded most of the video files onto the YouTube channel, or you can also, if you want, watch those videos if required. And some are like many programs are also shared on the Google Drive, right? So that also is already given to you. So you can just go through that particular aspect also. So this is all what I have for today. If you have any questions, either on the topic or on something else, you can raise. Otherwise, we can slowly wind up the check. So this is where it is right now, 19 students. So only 50% capacity. All right, so first we have to stop the presentation. Then